Aloha. Well, welcome back, everyone, and welcome to those who are joining us for our afternoon session. It's my honor to introduce to you all Zach Mermel. Zach was born and raised on Hawaii Island. He holds a master's degree in ecological land planning and design from the Keawanui School. He is the founder of the Ola Design Group, a hui of land design professionals devoted to Aina regeneration. Which he founded or co-founded in 2010. He earlier this spring had the honor of performing land consultancy work in Armenia through USAID. And Zach, you may have had the pleasure of taking a class from because he's been teaching agro-related classes throughout Hawaii Island for, I think, since at least 2012. So welcome, Zach, and I'll hand the floor over to you to introduce our next speaker.
Thank you, Lisa. Honored to be here to introduce Kimo Melcher, our intern this past spring and even this past fall. Born in Alaska and raised on the islands of Moloka'i and Hawaii, Kimo Melcher has always enjoyed hiking, volunteering, and the outdoors. After graduating from Kona Waiana High School in Kona and returning to Moloka'i to be closer to family, he was blessed with an invitation to participate in a permaculture design course that inspired him to pursue further education. After a year at Moloka'i Community College, he transferred to Hilo, where he found his true calling. Erosion on Moloka'i has been an issue for many decades. While working with the Spatial Data Analysis and Visualization Laboratory at Hilo, Kimo found himself looking at erosion mitigation structures through a geospatial framework. Kimo Melcher graduated from Hilo with a bachelor's in environmental science and is currently pursuing a graduate degree in the Tropical Conservation Biology and Environmental Science program, where he is seeking solutions to Hawaii's erosion issues with the help of SUAS and geospatial software. His professional internship project is entitled Locating Ideal Placement for Erosion Control Practices Using Remote Sensing and Geographic Information Systems, a case study in Keawanui, Moloka'i. The floor is yours, Kimo.
Sorry about that. Just trying to figure this out. All right. Oh, geez. And it's not on the right slide. Wow. I am sorry for the technical difficulties. It was bound to happen to someone today. And it was me. All right, I hope you guys can all see that and hear me. All right, aloha mai kako and welcome. My name is Kimo Melcher and I'm a graduate student in the Tropical Conservation Biology and Environmental Science program here at the University of Hawaii at Hilo on the professional internship track. I would like to start by thanking all of my fellow speakers, today's organizers, and you, our audience, for taking the time to join us here today. Mahalo. Today, I will be sharing my internship experience with the Ola Design Group and the work we did on Moloka'i in the ongoing efforts to find solutions to erosion in our partnership with Aina Momona. But before I begin, just a short overview of what I will be sharing with you folks today. I'll start with some of my backstory and a brief description of erosion. Then I'll introduce my research site and the organizations I've partnered with for my internship, followed by the goals of this internship project, the steps I took to meet these goals, and then I'll wrap up by detailing the results and outcomes of this work. And just a disclaimer, any image that is not giving a photo credit is one of my personal photos that I was able to take in these beautiful places I got to go. So when I was younger, I wanted to be a farmer. I had been waiting tables in Las Vegas and living with some high school friends, but I was ready for something new. And so I was born in a restaurant family, but I didn't want to didn't want to pursue a future in that. I didn't see a retirement there. So I began researching some of my interests, and this idea of returning home to Moloka'i to get closer to family and become a farmer began to take shape. And so I moved to Moloka'i on a farm where I hoped to learn what the life of a farmer was all about. While I was on Moloka'i, at that time, there was a lot of talk about genetically modified organisms, which deeply instilled in me this desire to learn to farm in a more sustainable way. So one day while I was hitchhiking, I was told that I should go and visit someone out in Mana'e on the other side of the island. After meeting and talking with them, I was invited to attend a 5-week permaculture design course where I learned about some of the environmental issues facing Moloka'i. And there was one which really resonated with me, and that was erosion. And it was there that the first seeds of my internship or project were planted when I was first introduced to the sediment check dam and erosion control structures, which I'll talk about more in detail later in this presentation. So at the closing ceremony for the permaculture design course, I was introduced to Uncle Emana, pictured here, where he's watching the sunset and showing off some of his throw net technique, when he and 2 other men came and performed hula for us. Uncle Emana was living on and caring for the Kahino Pohaku fish pond out on the east end of Moloka'i, as seen in this aerial image on the bottom left. After the permaculture design course ended, I paid him a visit at the fish pond, and I was invited to stay and work there with him and his crew. Since I wasn't born on Moloka'i and my father wasn't a hunter or fisherman, I jumped at this opportunity to learn these skills and help maintain the fish pond with Uncle Emana. So I left the farm and made my way to the fish pond to see what I could learn. So Moloka'i is a unique island with a strong sense of community, where many of its residents survive by hunting and fishing. And there is the saying that the ocean is our icebox. So many of the people take an active role in protecting Moloka'i from outside interests, whose ideas for economic growth would negatively impact Moloka'i's natural environment. And Uncle Emana was very involved in the community, and he would often ask us to accompany him to town meetings, where he would push us to pay attention and speak our minds if we felt the desire. It was there that I learned about the eating habits of monk seals, water rights, and various public plans or business plans that from those who saw Moloka'i as this untapped resource. And if I felt strongly enough about an issue, I would often speak up. But after a while, I started to realize that my voice would have more weight behind it if I had a college degree, and that with a degree, I could learn to better interpret and translate what was being said at these meetings as a way to help my community. So I began to take courses at Moloka'i Community College. So after a year at Moloka'i Community College, I transferred to Hilo, where I pursued a degree in biology. And soon afterwards, I met Dr. Rebecca Ostertag in one of her classes, and she gave me a summer job with the Liko Napilina project. And like those days are honestly some of my fondest memories. I really enjoyed weeding and gathering leaf litter in the heavy rains that happened every day while we were in these beautiful rainforests in Keokaha near the Hilo airport. And it was during that time that I was first introduced to this idea of the habitat suitability model, which was being used to locate endangered plant species specifically in the Pohakuloa training area. And this idea stuck with me, and I wondered, could these models be used, in another way to find areas that could promote plant growth and reforestation? And during the semester, I had a job with the Geography Environmental Science Department as a student assistant, where I graded papers and helped students and occasionally drove vans for field class trips. And it was on one of these field trips where I finally came face to face with one of these sediment check dams that I had been introduced to years before in my permaculture design course. And so within the Geography and Environmental Science Department, there was also the Spatial Data Analysis and Visualization Labs, which are led by Dr. Perroy, where they were using small unmanned aerial systems, or SUAS, and GIS, or in geographic information systems to track environmental issues. So with the introduction of these new ideas and what was possible with GIS, something in me just clicked. And these habitat suitability models, sediment check dams, and the capabilities of GIS, they all came together for the first time. I understood what I wanted to do. I wanted to do my part to find solutions to erosion with the help of these new tools and ideas that I had been introduced to in the ESTAV lab in the forest of Keaukaha. So I changed my major to environmental science, and I began focusing my studies on GIS and these other spatial technologies. And after I graduated with my bachelor's, I joined the TCBES program, where I began working towards this new goal. But I had much to learn about erosion and how I could leverage these new skills. Erosion. So as soon as the lands rose from the sea, they were met with natural forces ready to prepare them for life. So the accumulation of dust and debris and ammonia-rich bird excrement aided in the formation of soils, which is the foundation on which our forests depend. Erosion is a natural process whereby soils are broken down and forced downslope, where they accumulate and move through the lowlands and streams, eventually making their way to the ocean. This natural process has shaped our world by carving out rivers and aiding in the sculpting of mountains. Erosion is constant and always working in the background, slowly eroding the land through forces of wind, water, and gravity. And though it can be destructive, natural erosion occurs most often at a rate which is slow and non-problematic. But anthropogenic changes to the natural landscape can dramatically increase these rates of erosion, frequently to destructive ends. Modifications by humans to the environment often take the form of deforestation to meet the growing needs of agriculture, pasture, construction, roads, and mining. Without roots to hold it in place and foliage to protect it from the forces of rain and wind, soil is more susceptible to erosion, leading to increased occurrences of flooding, the loss of nutrient-rich topsoil, and sedimentation to ecosystems downstream. Climate change only magnifies these effects as rain patterns change, lengthening the dry season and intensifying rain events. So my professional internship was with the Hilo Design Group, a collaborative of Hawaii-based designers, horticulturalists, and ecologists devoted to enhancing food security and self-reliance through educational outreach, client consultations, and whole farm design. The objective of my professional internship was to help Hilo Design Group provide Aina Momona, a Moloka'i nonprofit who caretakes the Keawanui fish pond for Kamehameha schools, with recommendations to help slow the sedimentation of the fish pond due to erosion in the uplands. So the hills above Keawanui fish pond, which are also owned by Kamehameha schools, have been used as cattle pasture for many years. Additionally, goats and axis deer have found their way through the fences and freely roam the area, where they predominantly forage on the more palatable native plant species and where their hooves disturb the soil. So these changes have resulted in increased rates of erosion in the fish pond and the surrounding coastal area, as well as an overabundance of invasive plant species such as kiawe, lantana, Christmasberry, and haulikoa, whose scientific names I won't butcher and mispronounce for you at this time, who have taken over important habitat for native species. So the objective of my internship was to find solutions for erosion by bringing together all these ideas I had been mulling over for years. I wanted to simultaneously run two analyses on the hills above Keawanui. So the first question I had was, could I do a hydrological analysis from which I'd pull these longitudinal stream profiles that I could then use to locate areas where an erosion control structure, such as a sediment check dam or contour sandbag, could be placed to hold sediment? The process which I'd never seen done before and I had no idea how to do. So when placed across the waterway, an erosion control structure allows the gradual buildup of sediment and creates an area that is perfect for planting. And the second question I wanted to answer was if I could run a habitat suitability analysis to find areas in the landscape that could hold moisture thereby promoting tree growth and seedling recruitment. A habitat suitability model uses GIS to map environmental characteristics required for plant growth to help locate existing plants, or as I saw it, a tool to locate areas for outplantings. But to run these analysis requires high-resolution digital elevation models that are not freely available to the public. So the image on the right of the slide shows the digital surface model that comes from the County of Hawaiʻi database with a resolution of 10 meters. And the image on the left is a digital surface model with a 1/4 meter resolution that I generated over the course of this project. And as you can see, there's quite a difference. A digital elevation model, or DEM, is a digital representation of the Earth's surface, wherein each pixel is assigned an elevation value. And there are two basic types of digital elevation models, and they go by many names. But for the sake of this presentation, I will use the terms digital surface model, or DSM, when referring to a digital elevation model that includes the ground surface, trees, and buildings, and a bare earth model, or BEM, when referring to an elevation model in which the trees and buildings have been removed. Now, leaving only the ground surface. And so in order to run these analysis, I would first need to generate a bare earth model. So on this slide, as you can see, the approach that I took for this work, the first task was the lengthy process of generating this bare earth model. And to do this, I first had to place ground control points from which I had to gather their GPS coordinates. And I had to fly a small unmanned aerial system to collect aerial imagery. They took these photos and GPS information and used them to create a digital surface model and an orthomosaic. And then I did a land classification using that orthomosaic. And then additionally, I put the digital surface model through a process to remove the vegetation to create my bare earth model. And lastly, I ran my proposed analyses on this bare earth model in order to make recommendations for the ideal location for erosion control structures and outplanting sites. So in order to georeference this digital elevation model so that it was made to the correct scale and accurately positioned on the Earth's surface within a GIS, I had to include ground control points. And ground control points are identifiable markings with known GPS coordinates that are placed across the site before aerial imagery is taken. So on the left of the slide is an image of Avenza Maps, a phone app that allows you to upload georeference maps, over which it then tracks your position and allows you to create points. So the red pins are the locations of the ground control points that I placed, and the white squares are marks that I made to keep track of important areas, such as launch sites or interesting features in the landscape that I wanted to take note of. So to gather these GPS coordinates, we used a pair of Trimble R10 GPS units, which take advantage of real-time kinematics. So with real-time kinematics, we position one Trimble R10 over a known point and another over a new point. And because the RTK software knows the GPS coordinates of this known point and what corrections need to be made at any time to get these correct results, it also knows the corrections that need to be applied to this new point that you're gathering. So each morning we'd set up and turn on our first Trimble R10 over that known point we had at the bottom of our site, which then we'd spend the rest of the day hiking around the site looking for features in the landscape that we could use as new ground control points, over which we'd set up this second R10 and let it run for half an hour to gather information before heading out to find the next one. But once all the ground control points were in place and their GPS coordinates were gathered, we then began collecting aerial imagery. And so for this project, we flew the DJI Matrice 200 with a Zenmuse X5S camera and created our flight plans using the Maps Made Easy app pad on the app. So Maps Made Easy is a program that allows the user to designate the direction of flight, the height of the drone, the overlap between photos, and the total area for which you want to gather imagery. All in all, the ground control point and aerial imagery collection process took around 3 months to complete, sometimes put on hold due to weather and requiring many return trips to Moloka'i. With all the imagery, the aerial imagery collected, a sample of which is shown on the right of the slide, the GPS information gathered, I then returned to the lab to begin data processing. And for this step, I used Pix4D Mapper, a computer program that uses similar key points in adjacent photos to generate 3 main products. The first is a 3-dimensional point cloud shown on the picture on the left, which is an array of hundreds of thousands of pixels suspended in space, each with their own X, Y, and Z coordinates. The second product is a digital surface model, which I've touched on briefly. And the last is an orthomosaic, which is a large image that is stitched together using many individual images. So the first analysis that I ran was a land classification using the orthomosaic. Seen on this slide is an image of the NV software that I use for this process, a computer program that allows you to classify each pixel into one of 4 categories. Well, you can set whichever categories you want, but I chose to have 4 categories, and these were trees, grasses, shrubs, and exposed soil. This process involves selecting small groupings of pixels all over the map that I recognized as fitting into one of these 4 categories, which I then used the software to classify all of the other unmarked pixels. But before I could use this digital surface model in a hydrology and habitat suitability analysis, I first had to convert it into a bare earth model by removing the trees and other structures. And so I completed this work using Global Mapper, a software that takes every individual pixel and compares it to those around it. So if the elevation difference between a pixel and those around it is greater than a specific number, the software removes it from the model. And that creates these holes in the model, which the software then later fills by taking the average of the pixels around that hole in a process called triangulated irregular networks, or tinning. Now, on this slide, I have 3 images to show you, kind of explaining what tinning is. On the right is an aerial image from the orthomosaic, which kind of shows you this tree stand, so you can kind of understand what's going on here. We want to remove those trees from our digital surface model, which is in the center. You can see those trees standing out in the middle there. And then on the left side hand of left-hand picture, you can see the trees have been removed and they've been filled in with that tinning, which is giving us these flat surfaces. So when the bare earth model was created, I then moved on to the hydrology portion of my analysis. And this work was done using a software package called ArcGIS. And here I ran a sequence of tools that allowed me to delineate areas where streams of various intensities had the potential to form, as shown on the right, which in of itself is a useful tool to help land managers locate streams of high water and soil transport that could be targeted as waterways in need of erosion control. But I processed these further into longitudinal stream profiles, or graphs of elevation change along a waterway, an example of which is shown on the left, that I hoped would be useful in deciding where along these waterways that an erosion structure should be built. And I also had the habitat suitability model work that I wanted to do. Habitat suitability models are tools that can be used to identify various environmental factors such as soils, precipitation, elevation, or temperature as they change across a landscape. This tool has been used to find areas that could present a species range or to map the future range of species in response to climate change. Another product which can be created within the ArcGIS software. All right, so now on to the deliverables of my internship. Seen here are the first 2 major products used for my internship, both displaying the survey area in full, spanning from the road that runs along the bottom of the site, up all the way up to the top where the ravine kind of cuts you off there a little bit. Right, so on the right, we have the orthomosaic, which is a patchwork of smaller images combined into one large image. And on the right is the bare earth model, an image where the information tied to each pixel is not a color, but an elevation range. So this one is displayed using a color gradient that goes from black to white or from low to high elevation. Here is the land classification model I did. The camera used for this work captured imagery only using the red, green, and blue color bands, which made for a challenging task when it came to separating the shrubs from the shrub class from the trees and from the grass classes, as you can see in the lack of blue in this image. The issue was due to the stems of shrubs being similar in color to blades of grass and the foliage of shrubs being too similar in color to the foliage of the trees. So yet, despite these challenges and limitations, I was able to create a land classification model where the roads and trees are easily identifiable, even at the zoom level. And with continued collections of aerial imagery and geoprocessing, these initial land classifications can be compared to future efforts to track land cover changes over time. So the second set of deliverables I produced were those relating to the hydrology analysis that I had run. So shown here are the water pathways of moderate size labeled by stream order. And for this, I used the Strahler stream order method, a conservative method where the stream order only increases when two streams of the same order intersect. So this is one way to visually represent the intensity of water flowing through the area. So the higher the stream order, the more water passes through that pathway. So by looking at this image, we can tell that waterways colored in red, orange, and yellow are those that should, in theory, be pathways of heavy sediment movement. All right, so as I said earlier, one of the main goals for this project was to use GIS to find areas along the river's length where an erosion control structure would do well to slow erosion. And so to do this, I delineated the locations where high flowing streams would form. I used these to extract the elevation data from the bare earth model that I had created. And then I exported these values into an Excel sheet where I graphed them on a line chart to create a longitudinal stream profile, which I used to visibly locate areas along the graph where the elevation of a stream flattened out. And I targeted these as places where the erosion control structure might take advantage of the topography to hold soil. On the right of the slide is shown an example of one of these longitudinal stream profiles that I created with stars above the most noticeable flat areas. This information was then taken to ArcGIS and used to create the image on the left, where each black mark represents a location along a water pathway where one of these erosion control structures might be built. Here are the results from my habitat suitability analysis, or one of them. I choose to use the habitat suitability model as a tool to locate areas whose topography better protects the vegetation from the effects of wind and sun exposure. Areas that should, in theory, have higher soil moisture levels than the surrounding area, as soil moisture is thought to be one of the limiting factors to growth at the site. So the prevailing wind and sun direction on this site is east to northeast. So using ArcGIS, I located the west and southwest facing surfaces and those areas with gentle slope in order to isolate areas where these two characteristics overlap. The results of which are shown here in this image. Due to the prevalence of goats and deer in this area, outplanting should be protected by fencing. So areas outlined in this habitat suitability model that are close to trees would be ideal, as trees can serve as fence posts and would provide shade and leaf litter to further protect plants from the elements. Over the course of my project, I had some great experiences with outreach and opportunities to share what I've learned with some amazing people, and the pleasure of presenting the data collection techniques used in this project and some of my past work with Mr. Mack and his senior students at the Moloka'i High School Additionally, I led two great students, Kai'a and Daya, a pipes intern, and Evelyn Haas, a Moloka'i High School senior, through the initial data gathering phase of my project, which they both then had the opportunity to present to their peers. So it is my hope that the products of my internship with the Old Design Group aid in the restoration of the forests in the hills above the Keawanui fish pond, and that by doing so, the sediment of the fish pond in coastal areas can be reduced. Forests that I hope one day come to provide food for the local community and habitat for native flora and fauna. Though my college studies led me on a different path than the one I had originally planned, and I did not become a farmer in the conventional sense, I hope to remain on this path of a geospatial analyst to continue farming forests and working to help provide Hawaiian ecosystems, or help to restore Hawaiian ecosystems to a level in which they can provide for all. Over the course of my internship, I have spent many hours in the field leading small crews into remote locations where we had to accomplish a set of difficult tasks. And these were all new experiences for me that I had never led a crew before. And I was required to think on my feet and plan things out days in advance to make sure that we accomplished all our goals. So once in the lab, I spent countless days going through and processing data. And this internship has only cemented in me my admiration for all things geospatial. And I hope to find myself a job where I get to expand on these skills and continue looking for ways to address erosion. I hope in the future to continue to find ways to share these skills with others, such as I have had the opportunity to do with the students who accompanied me on my data collection efforts, and with this new high school student I recently met with whom I'm helping to design a research project. I'd like to dedicate this work to all those who have come before and all of those who will come after. And rest in love, Kailea and Brian. You are missed, but you will never be forgotten. You live on in us and through us. So I'd like to wrap up by thanking Dr. Ostertag and Dr. Peroi for all of their support and for the time and knowledge that they've given me. I'd like to thank Zach Mermel for taking me on as his mentee and letting me see the other side, the real world applications of this research. I'd like to thank Lisa Canale for all of her help and support over the course of my internship experience. I'd like to thank Kamehameha Schools, Aina Mamona, Uncle Walter, and Oboy Pedro for being so kind and welcoming and for allowing us to spend time in the beautiful Keawanui area. I'd like to thank Charlie Tommy for his help on Moloka'i and everyone else that I've worked with in the STAV labs, Nathan, Esther, Rose, Erica, and Roberto. I've had some great times. Mahalo to the Liko Napilina project, Nicole and Iz and all the others. I'd like to give a big shout out, a big mahalo to Pacific Island Climate Adaptation Science Center for the gracious funding for which this project would not have been possible. Just so much appreciation for all those folks there. And also to the Pacific Internship Programs for Experimenting Science, PIPES, for partnering me up with an amazing student in Kai'a, and of course, for the TCBES program and my fellow graduate students for making this such an amazing graduate experience. Mahalo nui loa. Thank you all for spending your day with us. If anyone has any questions, we might have a couple minutes. Otherwise, please feel free to send me an email with any questions you may have. Thank you. I don't know, I can't hear you, Lisa.
Shoots, I did it again. Thank you, Kimo, for a fantastic presentation. We do have time for a question, so if somebody could just unmute themselves and please ask away.
Hi, this is Walter Reedy on Moloka'i.
Hey, Uncle Walter.
How's it? So we're ready to go up Mauka and stop that dirt from coming down the hill. And we're really going to need help to figure out where we're going to put all of the stops. We're cutting mangroves, making them into long bales like the skinny mangroves, tying them up into bales, and we want to put them into the ravines or where the water is flowing down to stop it. And we want to throw seeds in there, hoping that the seeds will start growing stuff in these places. But we saw in your presentation that you had picked certain areas that might be good places to try and stop that water from coming down. So we would really appreciate it if you would work with us so we don't put them all in the wrong place.
Yeah, I look forward to the opportunity. Yeah, I mean, I'll be presenting this information in a more detailed presentation to the folks at Imamona, and we can talk about areas we want to focus on, and we can kind of go from there. But yeah.
Okay.
So, looking forward to it.
Great.
Sure,
Did you,
thanks for
get back,
listening.
did you get your drone back that we found?
I did. I'll have it back next week.
Okay, right on.